So welcome everyone to this month's researcher-facing call on containers. I know we've had presentations about containers before, but I think it was a couple years ago, so we thought we'd revisit the topic for everyone. There's a lot of you on the call, so the format we're planning to do is we have a few presentations on sort of different aspects of working with containers, and I'd encourage you to put questions into the chat or comments. I'm hoping to have a little time after each presentation to address questions and have people share their experiences. We may have to mainly do that via the chat because there's so many people on the call, but we'll see how that goes. So our first speaker is Jeremy Fischer. So Jeremy, I'll turn it over to you and you can share your screen.
All righty. There we go. Okay, so the first question I have to ask is, are you seeing my presentation view or are you seeing the correct view?
Correct.
Excellent. It's always a crapshoot. I don't know why Zoom likes to switch back and forth on me. Let me get my mouse in the right place here. There we go. All right, I am Jeremy Fischer. I am the manager for the Jetstream Cloud, which is an NSF project at Indiana University. I'll be talking a little bit on introduction to containers, just a quick overview, giving people some background before turning it over to the people that actually support the researchers on it. So the path getting here has been a fun one. I'm a sysadmin by training. I'm learning to love containers in all their forms. But to give kind of a background on where things came from. So it all came from a very simple idea of giving people a place where they can work without messing with the rest of the system. Basically locking things up into a change root jail or to root jail where people could make changes to their environment and not impact the server as a whole. That way they had a controlled environment without crashing everybody else. It evolved over time. So you started seeing projects and products like vServer and Solaris containers, OpenVZ, things like that can process containers by Google. But it evolved eventually into a thing called LXC, Linux containers. And that's kind of where we saw the first basis for Docker. This was the first sort of container system that didn't require kernel patches. So you could make it run pretty much on any Linux system without a whole lot of pain and suffering. And this evolution into Docker is really kind of what made containers popular. It was a combination of the right tool at the right time, ease of use, and frankly, some marketing. The biggest potential downside for Docker is it has to run as root. And obviously, most of your friendly neighborhood HPC folks are not going to let you do that. So we started looking at other things to allow people to run containers in an HPC environment. So they could scale up from their laptops or from virtual machines and things like that. And that came into a few different technologies. Started seeing Shifter and Charlie Cloud and Singularity. And I'm mostly going to talk about Singularity. It's not a whole lot of talk, it's a slide. And some other folks behind, that come after me will probably talk about Singularity because that's probably the most popular means of running containers in HPC these days. You start seeing a lot of things. Charlie Cloud, for instance, you see at Los Alamos. That's sort of their default in-house thing. Shifter was born from Docker code as a project between NERSC and Cray to kind of scale containers in HPC workloads. But basically, the concepts are all the same. So the things that we might talk about today with Singularity are most likely going to apply to the others as well. And then you started seeing people kind of up the ante. So you started seeing orchestration with that. And some of that came in the form of using Docker Compose to be able to script your container loads, of seeing things like Docker Swarm and Apache Mesos and Kubernetes to orchestrate the life cycle of your containers, about being able to evolve and grow dynamically and shrink dynamically and be able to rise to the occasion of running whatever workflows you have in your containers. So the why comes down to a few things. So consistency. You always have the same software stack every time you run. You don't have to worry about what's the system been done now. You don't have to worry if you're running locally that security patches come out and changed a version and now it no longer works. If you're a Mac user, you know the pain and suffering of the Python 6 package changing every 10 minutes and being outdated. You have Portability, you can easily move from place to place. So if it's done properly, the size of your containers can kind of be controlled and you can easily move things around. You have just-in-time fast boot. So they're ready almost immediately. They're easily dismissed, easily updated, and easily redeployed. Small purpose-built containers that have a single or at least an uncomplicated function, these can be maintained pretty easily and changed as needed without having to redo the entire stack. So it fits well for doing things like microservices. And as we all run into on the HPC side, if you support biology folks especially, you often run into legacy code, things that were made to run many years ago and they still need to run today because maybe there isn't a better tool. But maybe you have some difficulties getting it to run on modern operating systems. So it's a good way to make things stay self-contained for some older things and not be the security risk of running an older system out there. But it's always something good to note, simple versus easy. The process is simple, it's not always easy. So talking about containers versus virtual machines. So coming from a virtual machine resource like Jetstream, we're used to seeing VMs as completely self-contained things. They have everything. So the operating system is there, all of the libraries are there, everything is there. It's completely independent of the host. So the host can be running, it can be a Microsoft hypervisor running Linux. It can be a Linux hypervisor running Windows if you're into that sort of thing. But basically the entire operating system is there. All of the resources and tools you would get from the operating system are there, as opposed to containers. So a container has a smaller footprint. It depends on the host operating system to give them part of what they need to run. So you need that Linux kernel to be able to run your Linux container. You aren't easily able to run different operating systems on a host. Now, you can say, hey, but I can run Docker on Windows or Mac and have a Linux VM. That's true. It's actually running a small hypervisor behind the scenes. So it's one of those things that containers, to maintain that smaller footprint, depend on having part of that host operating system available to them. The other part is, as I note, there's a very robust ecosystem of many pre-made containers are available through the various hubs, which we're going to talk about right now. So what is Docker? It's most likely going to be the most common container infrastructure that you're going to find. So like I said, it was originally built on LXC Linux containers. It's parted away from that original architecture and they've gone to their own code base. The kernel usage is what makes it both light, but it's also potentially dangerous. You're not entirely isolated from the host like you would be in a virtual machine. It's a little bit of a trade-off. However, in the grand scheme of things, it's mostly safe enough. Problem is, again, since it does require having root privileges to run, you are running as root when you run Docker, there are potential security issues there. Hence, we see some of the other container options that we're going to talk about in a minute. But basically, it's a very simple system. You have a client. It talks over a REST API to a server. It does its things either locally or remotely, depending on how you're configured. And then you use a large public repository of objects or a private repository where you have containers and images, for instance, at Docker Hub, and other repos are available where you can pull those down, use those how you need to, modify, save, build your own. Basically, it just gives you an infrastructure. Docker gives you the infrastructure to manage, deploy, and reuse containers and share them rather easily. So kind of the big picture. So you have your Docker client, like I said, and that's, typically you'll be on a laptop or on a VM or something like that. You talk to the Docker daemon, which a lot of cases is actually running on the same host where you are. And then you pull things from your registry, and that can be, for instance, Docker Hub or Ubuntu or Nginx or whatever it might be. You pull those down to your host to work with them however you need to. And it's making all those calls via RESTful API. So it's something that's important to know that when you talk to the registry, you pull images, and that's basically a read-only template. And those are the instructions for creating a Docker container from a registry. The default is Docker Hub. Like I said, there are many you can choose from. There are other public ones out there. You can set up private ones. A lot of institutions, especially with Docker Hub's changes lately, have set up private registries to get around the usage limits at Docker now. But it's a very key concept of images versus containers. Images are a read-only template for creating a Docker container. It's basically a snapshot of a container. Containers are the runnable instance of an image. And a nice graphic on how Docker's used. So again, you see at my computer, you have the registry that's out there, you pull things down, your image is there, you can run it and have your running container, you can manage the container, you can change your container, you can use a Docker file to build a container. We actually do a tutorial at PERC, we did last year, and then one at Gateways, and we've applied to do another one for this upcoming PERC on a deep dive into building and using containers. And that includes the Docker file and how that works into it, and the Singularity framework and all that. So this graphic just gives a nice overview. So what is Singularity? It's another container platform. And the reason we talk about it is Docker was created with a single host or single user in mind. So it needs to access the host machine's kernel. It needs to run with escalated privileges. And basically when it comes to wanting to scale workloads up, if you want to move to an HPC cluster, since I don't know any super user that is going to give you root access, you either have to find a way around that, or you have to get used to running your workloads locally. So Singularity was created to run containerized applications in HPC environment. It's probably the most popular of the ways to do this. And the key difference between Singularity and Docker, what makes it very different, is untrusted users can run untrusted containers on HPC. You don't have to have any special privileges. Your container processes run as you, and you don't receive escalated privileges, which should keep containers from being a security issue. Singularity complies with the Open Container Initiative as well. And so that concentrates on the start for interoperability with Docker. So you should be able to take most Docker containers and run them under Singularity. So you don't have to reinvent the wheel if you find a workflow that works for you in Docker. This is a shameless plug for one of my fellow speakers and for one of my co-authors on the tutorial we do, which is talking about XCRI. And they also provide researchers with some assistance in helping build and maintain containers for their scientific workloads. So there is a place for some support, and you can always talk with them. If you have questions or comments, they're reachable via Exceed and help@exceed.org. And onward. I tried to keep it simple and fast so I wouldn't take time up from the folks that are really out there doing the hard work of supporting the researchers on containers. If there are any questions before we move on, please fire away.
Yeah, thanks, Jeremy. If folks have questions about sort of this intro about containers, basics, please feel free to pop them in the chat. There was a question about, I think, some other different container adjacent services, Wholetail, CodeOcean, and Binder. I do want to keep moving on, so if folks have thoughts or input about that, feel free to drop those in the chat. Yeah, Jana, did you have something to add? I saw you wave, but I don't know if that was.
I was just fluffing my hair.
All right. And thanks, Jeremy, for the note about the slides. We will try to have the slides in the Google Doc after the call ends so that people can access them later. All right. So we're going to move on to our next speaker, Anna. So we'll turn it over to you and go ahead and share your screen.
Great, thank you. Let's see. All right, I think I'm sharing the right thing. Okay, well, thank you all so much for having me today. My name is Anna Sackmann, and I'm the Data Services Librarian at UC Berkeley. And today I'm going to talk about a survey that Amy Nizar and I administered to learn more about how researchers discover and select VMs and containers. And thank you so much to Jeremy for providing some really excellent information. I can skip all of that from my part. Before I jump into the study, I'd like to provide a little bit of context for why we did this. So at UC Berkeley and really beyond, we've seen a big increase in the numbers of researchers who are relying on virtual machines or container images to support their research, computations, running analysis. And we know that there is an increase in need and usage, but we don't know how researchers go about discovering the right image, and we don't know what characteristics they look for when selecting their image. So Berkeley Research Computing began thinking about this maybe 3 or 4 years ago. And Amy and I were recruited to explore this and find answers, partly because we're librarians. And this research project is one of the ways I think that really shows the importance of a good collaboration between research IT and libraries. So after getting IRB approval in the fall of 2018, we held focus groups to gather some preliminary data. And in order to widen our pool of responses, we sent out a survey in the spring of 2020. And we wanted to learn a couple of things. We wanted to learn where and how researchers are searching for VMs and containers. We wanted to learn if more computationally savvy researchers who are using computational resources beyond their own machines, if they're searching for VMs or containers, what are they looking for when they're searching? And what do they value? What are their different values for what they're looking for? So one of the first questions we asked was about search behavior. And out of 141 usable responses, we learned that 20% search for images in a variety of places, namely starting with places like Docker Hub, AWS, GitHub, and Google. So now 20% of 141 is not a big number, but that doesn't mean that the other 80% of respondents aren't using VMs or containers at all. One of our goals was to learn about the behavior of respondents in different disciplines and roles, but due to some incomplete responses, we were unable to collect usable data in all of the areas that we were hoping to. So we decided to use incomplete responses because this is really just an exploratory study for us and our services. And so we felt okay doing that. So following our general searching question, we asked if respondents were using computational resources beyond their own machines. And a little over half said that they were not. And the two reasons that stood out was that their work didn't require additional resources, or that they needed resources but didn't really know where to go to find them. .24 of the 51 respondents who do use computational resources beyond their own machines are using Savio, which is a Lawrence Berkeley National Lab and UC Berkeley supercomputer, or they were using Savio plus some additional computing resource. And now I'm going to talk a little bit about the characteristics of VMs and containers that researchers found the most valuable, or that we learned they found the most valuable. And I'll go deeper into each of these categories, but here's just a brief snapshot of the top 5 that rose to the top. They look at the software they can run, the trustworthiness, ease of use, reproducibility, and how well supported the image is. So we developed a list of characteristics based on what we learned from our focus groups, and also from brainstorming, reading, and research. And we asked respondents to select which characteristics they most valued based on a 5-point Likert scale, ranging from not at all important to extremely important. And because we do have some incomplete data, we weren't really able to make any definitive findings about certain populations like faculty. So we decided to focus this mostly on graduate students. This is the population that we had the most data about, and we find that we can actually make some more interesting claims about these folks. So the first characteristic is software, and we use the definition at the top of the slide. So VMs are containers that are ready to run specific software applications or be augmented with additional software and have been patched. with this graduate student population, 82% of them think that this is either important or very important. And we have it further broken down on the right, as you can see. So 53% of those think it's important and 29% think it's very important. The second characteristic was a trustworthiness. And I think this one is actually very interesting. And we defined this as an image that is built or recommended by someone the researcher trusts, is secure and free of malware, and has a recipe that describes the environment. So 82% of the graduate student respondents think that this is important or very important. And again, we've broken it down here on the right. The third characteristic is ease of use, or images that can be used with a graphical user interface or used as is, meaning that the researcher doesn't have to build and compile their own image. 59% of the graduate students found this very or extremely important. And again, we have it broken down on the right. This was pretty interesting to me, and it makes me think more about our pool of respondents and the people who elected to take the survey. These are people who are probably already working with VMs and containers, and potentially already have a higher level of technical capability. Next, we have the characteristic of being well supported, which we define as images that can be set up for access by multiple users, or is run by lab or run by a lab or campus, and is familiar with the technology. And 41% of our graduate students found this very or extremely important. And this breakdown was a little bit more uniform with extremely, very, and moderately important. As librarians, we were very interested in this reproducibility characteristic. So we defined that a little bit more broadly, just as images that are reusable and citable in terms of how they're discovered. Does it have a citation or a digital object identifier that comes with it? And 18% of the graduate students thought that it was extremely important, 36% thought very important, and 26% of them think this is moderately important. This was encouraging to both of us to know that people are starting to think about this and think about containers and VMs as yet another research output similar to data that can be archived and used in the future. And it's something that we're thinking about a lot at UC Berkeley, how we preserve these for future use. So our next steps, we wanted to interview researchers by Zoom who agreed to speak more about their responses. That has not yet happened, and that's okay. We are also sharing the results, and we're sharing our Qualtrics survey with other colleagues in the UC system who are interested in conducting this study on their campuses, so that as a system of 10 campuses, we can gather more rich information and take a more centralized approach to how research IT organizations and libraries approach VMs and containers. So that is it for me. And yeah, I'll pass it off to the next speaker or for a couple of questions.
Yeah, thanks, Anna. This is really cool to see someone actually looking into how researchers' concerns about containers. And I think the kind of characteristics you highlighted are all things that it's good for certainly us as support professionals to think about as well. Does anyone have any questions for Anna specifically about this talk or the study?
I have some questions, Christina.
Yeah, go ahead, Jeff.
So thank you for presenting this. It's really interesting. And I already sent a note to you and Amy to get some more information. But I was wondering a couple of things. First question is, how did you select your audience for this survey? And the second is maybe just your opinion on sort of the state of readiness on your campus, or maybe even in comparison to other campuses, for moving to more containerized workflows?
Very good questions. I will, I'll address what I can and then pass it off to Amy if I've missed anything. To address your first question, we had to be very careful with the IRB because we wanted respondents to remain anonymous. So we used our connections with the subject librarians. We reached out to them and asked them to send out the survey along with a message, and we did a little YouTube video explaining more about our study. We had the subject librarians then send it out to graduate student and department listservs. So we didn't know who was on those email lists, but which ultimately is a little bit hard because we don't know how many people received the email. So we worked through our subject librarians. And then to address your second question, I don't think UC Berkeley is in a good place right now to provide these services, but it's on our radar and we're working on it. One of the first people in our focus group who we spoke to a while back had just come from MIT, and he was like, well, they just take care of this for us. And it's just a service that the university provides. And then he came to UC Berkeley, where it's kind of like you're a little bit on your own and at the whim of your research group and department to a certain extent. But we hope to be providing more support in this area in the coming years. Does that answer your question?
Yes, thank you. And we'll be in touch, Hannah.
Great, thanks.
Yeah. Amy, anything to add?
I think the only thing I would add is that, you know, we're still gathering data in order to determine our readiness. And I put in the chat that we're working with a few other UC campuses. UCLA and UC Riverside have expressed interest in conducting this on their campus. And I think if we can gather more data as a UC system, we can make a stronger case for readiness and perhaps even doing this type of work together.
Count me in on that too, Amy.
Yay, welcome Santa Cruz.
All right. Thanks, Anna. That was, I think, a great introduction to starting to think about researcher concerns and supporting researchers with containers. And I think Peter is going to continue in that vein, if I understand correctly. So I'll turn it over to him.
Hello. Yes, I am going to continue in that vein. Are you seeing my slides now? Uh-oh, I think I froze. Can you hear me?
Yeah, we can hear you. Yep, and now I see your slides.
Okay, sorry, my computer froze there for a moment. Okay, so I am going to continue in that vein, and I apologize if folks are already more familiar with containers than these slides will present, but I wanted to kind of go off of some of the materials that we were using in our container tutorial for PERC that Jeremy mentioned, and not assume anyone already is super familiar. But I'm working in the I'm working in the Center for Advanced Computing at Cornell, and I'm also an XCRI engineer, which is part of what Jeremy mentioned on the team. And we're actually building containers for researchers to use on Exceed resources. And I'll talk a little bit about that as well. But that's kind of where the angle I'm coming at this from. And I kind of wanted to focus on how containers actually meet researchers' needs, and then some of the lifecycle, deploying, security, next steps. But I'm not going to go too deep into anything specifically. So just kind of giving you an overview. In particular, I wanted to say that researchers have needs that containers can meet. And when we're trying to support researchers, it's helpful to know if they're coming and asking you, should I put this in a container? It's helpful to know why they're useful and what the effect is. You may notice on the left, I didn't actually include scalability. There's a lot that could be done as far as performance, and there are a lot of papers about it. I can talk more about that if people are interested in the question section. But in particular, it helps to have working code at a stable point. You can reproduce that same workflow for different experiments, and they're ideally easy to use. It's one new tool or possibly multiple to learn, but after that, it can be quite easy to work with. And once someone has a container that's already built and running, it's a lot easier for other people to pick it up and start using it. And and it kind of can contain encapsulate the whole process from building and compiling your code all the way through to capturing the data, visualization. There's a lot of different tools that are containerized for those kinds of things as well. It's not going to the next slide. Sorry. Okay, and I think one of the major things that's often overlooked is that containers are useful as a tool for releasing new versions of software or for distributing software to users. It's become kind of a larger method within industry to do that. And you can tag, you can pin versions and things like that. But there's kind of two different ways to use containers. And if you start using containers at the production level, as in this is often how you see in scientific computing, people will pick up code and they want to just start running with it. But often containers that are used for developing that code look a little bit different than the actual production. And there's kind of a different design process involved in how you produce those kind of containers. And so a development container typically has, some editing tools and dependencies and maybe VNC and data visualization in it that you don't actually need when you're running on a high performance computing resource, for example. And you kind of want to pare that down when you're actually running your code and things like that. And And a production container ideally is more lightweight. Especially, actually, it's more important that your production container is lightweight if you're starting to use something like Kubernetes in the cloud, which is becoming more popular for scientific computing applications. But with a development container, you have code that's changing, it needs to be updated, whereas a production container is more static. And so there's kind of a different philosophy there in how you produce those containers. And so you might start with a development container, pare it down into a production container before deploying on a resource for computing. And data management is kind of a major factor here with containers. So there are different ways that different container technologies do data management, and this can be kind of important. So Singularity has access to the root file system. Docker does not have access to the root file system. You can use a few different ways to create that access and determine how much access you want or which particular files or directories have access. But there's also, as Jeremy mentioned, kind of a different way they interact as far as the daemon is concerned. But it's useful to know going into working with researchers on with their data, how they will be able to access their data, how much data they need to move around, and ideally you're not putting the data within the container, so it can be really helpful. So here are some of the different data management paradigms you can use within Docker and within Singularity, and hopefully these slides we can make available, but if not, I'll have a link at the end for where the larger set of slides for our tutorial is, so you can get these links. In particular, I've used a lot of bind mounts, and Singularity's direct access to the root file system has been really helpful for large data use cases like a radio astronomy case I'm going to talk about next. And just kind of to give an example of a container that we've developed for scientific researchers, for scientific computing researchers. Working with a group at Cornell of radio astronomers, they're working as part of Nanograv, and they're working with they're searching for fast radio bursts and pulsars and lots of data, previously using Arecibo. Arecibo is now non-functional, so anyway, still have lots and lots of data left over from it, and there will be more data coming from other sources. So lots and lots of data, and so data management is kind of a large issue. And we started with a container that Nanograv actually built called NanoPulsar. This actually includes Python, R, and more, and you can actually go see, there are links in all of these slides for each of the containers I'll talk about. but started with pulling originally a Jupyter container. Nanograv started with pulling a Jupyter container. So Jupyter built this container and supported this container. Nanograv added their code to it. And then it, after a year, it had to be updated and it didn't build. So we made a new container that did build. And that was for the Aristotle Cloud Federation project. And it can get quite big quite quickly when you're adding all of these different kinds of codes and trying to work with them. So we ended up paring it down to a smaller version, and there's a Docker and a Singularity version. And the Singularity version is actually being run on Bridges, now Bridges 2. They're moving to Bridges 2 with this container. So these are some actively used containers as well that you can look at if you need some examples. Reducing container sizes becomes more important if you're working with Docker, in particular in the cloud, as I mentioned. So I'm not going to dig too deep into this, but just be aware that each layer can add more and more size to your container. So if you want to move this around, if you're doing a lot of moving your containers around, it can be something to look into deeper, and some ways to reduce your container size. Excuse me. You can use pip to reduce, so it's all in one command to install a bunch of packages if you're using Python. And if you're, kind of reduce or combine your number of run commands, you can use multi-stage build, which leverages the Docker build cache. And don't install what you don't need. Again, that goes back to the development versus production philosophy. And sometimes people do multiple decoupled containers using microservices and things like that as well. So the best practices for uploading these containers when you've built them is you don't want to upload private data. It's important for research. So most of the places where you can upload the registries that we talked about earlier, there's a lot of public ones. If you're working with private data in particular, you don't want to upload it, but especially private or licensed software, this can sometimes be a concern. Sometimes you want to distribute parts of it. You can make a public image for the parts that you can distribute, but be aware that any licensed software, even if it's open source, should include a license and things like that. Again, these are some of these things underlying our software best practices, but they follow along with containers as well. Documentation is helpful to include, but not necessarily if it's a huge pile of documentation. But again, a lot of people hook up their GitHub repositories to their Docker Hub or Singularity Hub repositories, and their images are connected. You can look at the Docker file or Singularity definition file, and that can be really helpful. So when you're actually going to deploy these containers, moving from, if you're moving from code you've worked on an HPC machine to the cloud, it can actually add some complexity. MPI in particular is where a lot of people end up having issues, whether it be with networking or scalability, and setting up containers can often require orchestration of some kind. And then again, data management. Docker doesn't have the same kind of philosophy about access to data, and so you have to set something up to access your data in the cloud. And so there's different paradigms for that as well. But using Docker is kind of the standard for cloud. If you are going to deploy in the cloud, public cloud providers offer some managed services that you can use, and container orchestration options abound, but it's often considered easy to use, and there's lots of forums and questions and answers online you can find. But security is also a concern when deploying in the cloud. But again, there's more and more work on this. In particular, we have a paper from Berkeley last year that you can take a look at of some example containers we've deployed in the cloud, including MPI workflows. And then when you're deploying a container on an HPC resource, it's a little bit different. Again, Singularity is dominant within HPC right now, other than some of the examples that Jeremy mentioned. But in particular, it can kind of simplify getting started if all of your code is already in a Singularity container. And if you know how to use Singularity, obviously you'd have to learn it, but you don't have to install things to your home directory, particularly if you have specialized code. You can just put it into your container. You don't have to pester sysadmins if they don't have your dependencies as part of the container, as part of the environment already. And Yeah, so using Singularity on Exceed, we focused on providing Singularity containers for the XCRI project, and Singularity because it's available, it's secure, and it's available on all the tier 1 Exceed resources. So that's what I mean by it's available. You have bind mounts for easy data access. Static. The container is actually static. This is worth noting. There's no overlay file system, so you actually end up kind of with the more production paradigm on Exceed resources with Singularity containers. But in the MPI major version in particular has to match if you are using something that uses MPI and just the major version itself. And so that can be a headache if you happen to use different MPI version than what you're loading into your environment, but that's worth noting. But job scripts and bind mounts can vary on different systems. So particulars of your system you should look at with your resource. And then security, obviously we've talked about this a little bit, but Singularity is often used for sensitive systems because of the root level access concern. Although I do want to mention that Docker does now have a rootless mode, and it was previously not supported by, it was kind of like in development, but it just recently, as of like 2 weeks or so ago, was announced that it's now supported. So there is some chatter about whether that will be something people can implement on HPC systems, but essentially you can run the Docker daemon without root access. You can install Docker and run. And so there's some docs on the rootless mode that Docker provides, and there's also a doc, but there was a talk about it at DockerCon 2020. If you are having multiple users, you kind of start with, it's important to note that for security, you should probably set up, same as you would on any other shared system, different users and privileges and things like that. It's worth noting that the default user in best practices for Docker, they usually recommend you set up a user for your container. Singularity recommends if you convert from Docker to Singularity that you actually only ever use the root user, because Singularity takes the root user as the user of the system. So, say your username is Pete, because I'm Pete, and I am on a system, my Singularity container would take the root user of the Docker container, and that would become Pete. So there are different best practices for building Docker containers for Docker and for Singularity. So that's worth noting. If you're using Cloud VMs, there's firewalls and security groups, and limiting SSH access is probably the best way to secure your container, because if they can't get to the VM, they can't get to the container. But also they're paying attention to what the public image contains. It found it interesting that it was just mentioned that people are concerned about security within their containers. That's good, but not wanting to build it yourself can be the best way to not know if it's secure. Building a container from a trusted source is probably a better way to ensure that it's secure. There's a lot of companies that have their own verified versions of containers on Docker Hub that you can start with as a base image and add your software to. And then I just wanted to put a quick plug for the XCRI project. We actually do have a paper talking about how we create reproducible containers and that project. And so that's linked here. And briefly, I'm sorry, I'm taking a long time. I want to briefly mention that container orchestration is kind of becoming more and more popular, getting more and more attention, Kubernetes in particular in the cloud, but there's also Terraform and Ansible and Docker Swarm as well. Docker Swarm is usually for Docker Swarm and Docker Compose are for simpler cases, but if you're looking to do HPC clusters in the cloud, you're probably looking at something more like Kubernetes, maybe Terraform, Ansible. And again, we talk about Terraform, Ansible in this paper, and we do have an upcoming one where we'll talk about Kubernetes. And then just a link to that container tutorial we've mentioned a couple times that Exceed provides. And I'm sorry I talked so long, but if you have any questions, please let me know.
Okay, that was great. Thanks, Peter. So yeah, there have been a bunch of questions. So one thing I'm going to ask is that if anyone has links or resources, if you can't access the doc, put them in the chat and we'll put them at the end. I put like next steps, learning more. So like share your tutorial, or where to go next is what I called it. So share your tutorials and your things that have been useful for you. It'd be great if we could build up a list of resources for folks. Peter, there were a couple questions in the chat as we went along that I wanted to highlight. I think Annalie's question about size was answered by people in the chat, but there was a question about, is the container usually used in the HPC environment as a black box where data is read in from outside the container and then computational results are written as well? Can you speak a little bit to how that happens? And then anyone else from our speakers, Jeremy or Anna, if you want to chime in as well, feel free.
Yeah, that's actually a good question. I would actually argue that Docker is more often used as a black box in the cloud. At least when we're doing scientific computing, we often put a script, run it. But in an HPC environment, you can directly, it feels more natural to directly interact with your container. To hop into the container, you don't feel like you're leaving the system. And I think that a lot of that is because you're integrated with the file system with Singularity. So I wouldn't really consider it a black box. You're probably compiling your code and putting it in there as part of your build process. I think that there's a strong connection between if you're the person who's written the code, building the container. So I think if you're building software, it's really useful right now to be aware and understand containers. So it doesn't feel like a black box because I don't think it should. It's kind of, you wouldn't want your own laptop to feel like a black box, I guess. But with things in the cloud, it's more often automated. And that's why I think it can be a little bit more of a black box. I hope that helps to explain.
Yeah. Other additions from Jeremy or our other speakers?
Hi, I had a question about just the difference. For Docker versus Singular, when you do have persons using Singular who are collaborating and want to integrate any kind of changes to code or script, is there a process, a layer of approval that Singular users have to go through compared to the Docker users?
Where you're like modifying a container?
Yes. If you're modifying a container using Singular and you want that integrated, is there an approval, like a level, a layer where there's an approval that has to happen from someone who does have access to that more sensitive, I guess, integrated code or script?
Mm-hmm.
I think, so if you're a user on a system using Singularity, the restriction comes with you don't have access to the root file system. Right. Sorry, you don't have access to, as a root user, to the system. But there's not really restriction to the container. So if you're a Singularity user, then you're either using a public, an image that you have from someone else, or maybe you're building it yourself. In the case of pulling an image from a public resource, you don't really have access to change it other than adding to it, but you don't have any access to change the build of the container unless you have the source. And in the case of Singularity, the source is called the definition file. Sometimes you'll see it called the recipe file, but in Docker, it would be called the Docker file. And then you could rebuild from there. It's generally best practice to edit the build rather than the live container because it's not retained. The changes that you make to an active container are not retained. But unless you're restricted, unless your access to a container is restricted because you're given a user, sometimes research groups will have, this is our container, we have it hosted on a VM and everyone can access it. I've worked with a group that's done that before. And so unless they restrict your user's access to the container, then no, you should have kind of freedom with the container itself.
Okay, so Singularity will never be used with a collaborator that you want to contribute to the build. It will only be used for someone who you want to have public access to that image, but
oh, I see.
That was my question. I know there are situations where you may be an organization and only organizational members can access root or be allowed to, or be granted access to be added as a root user. You can't do that with Singularity. I guess that's the question I'm asking. It's just you would only use Singularity in any event where you don't want any changes for outside users outside of your organization.
I think it could be used for development. I think that maybe you would want to do development in an environment where you can make active changes to the container and save your changes by making changes to the build. But on a
Yeah, so Kimberly, I'll say that, you know, a container image, if there's like an authoritative image that like your group is producing, whether or not people can change that depends on who can access where it's being published. Like if there's a central location, that has nothing really to do with Singularity or Docker, but just like who has the right account. Anybody could access that container image and run it on their own computer, say with Docker or on a resource that has Singularity. So there's a little bit of a distinction between those two things.
Okay, thanks.
But yeah, I'd be happy to follow up more. We are out of time, and there were so many great questions in the chat and good responses. So we'll be saving the chat and trying to integrate it into the notes. So definitely thank you to all of you who chimed in with answers to those questions. If you have more questions, throw them in. I think our speakers, some of them were willing to stay a little bit after to chat further. I see Peter giving the thumbs up, so feel free to do that. And I'm going to turn it over to Jana to kind of do our wrap up. Thank you all.
So yes, and if you do get a chance to revisit the document, so for people who struggled with editing earlier in the process, I just especially want to encourage you to come in and do some voting. At the top of the document, we have a list of future topics. So please just go through and add +1 to topics that you would find particularly interesting. Our next meeting is March 11. And if you weren't able to sign in earlier, please do try to do it again. If we do not currently have you on the mailing list, we will add you to our mailing list so you can stay in the loop. Today's topic was supporting researchers with containers. And special thank you to our presenters today. So we had Peter Vaillancourt, Anna Sackmann, and Jeremy Fischer, who presented, and Eric Coulter as well. This call was recorded, and the recording will become available. And when it is, we will email out and let you know how to access it. A note, PERC 21 is actually going to be coming up, well, when it's not so cold. I'm looking out at snow outside. But even though it's a little ways away, the deadlines are coming up, and compared to last year, we've been informed that this year the deadlines are hard deadlines. So full paper submissions for PERC 21 are due March 9th. So you might want to put that on your radar. Additional submissions are in April. Panels and birds of a feather are in May. Go ahead and check that out at the PERC website, the calls for submissions. All right, and I want to just thank everyone for attending today. And I want to thank the people who worked on the call. So that's Claire, Christina, Werwan, Martin, Annalie, Amy, Katya, Bob, and I'm Jana. See you guys next month. Bye-bye.
Yeah. Thank you, everyone. Thank you to our speakers.